Recording has started.
I tested this. This is working. So I guess if you open, you know what you want to open.
It doesn't work on PDF.
It should.
Okay, let's try. You go to views. So slideshow. Okay, now if I want to go. Okay.
If you hold this down, that's it.
This go back.
Yeah.
If I hold. Oh, so we should change. Okay, now if I go. Oh, it works like a charm now. What you done? Shake it?
She's ready to share, I guess. Yeah? I just charged it up, but I'm saying no, it should work.
Yeah.
I think she's ready.
Oh, yes, it's.
Should we go together?
Yeah, I can. Is yes, time. Hi Anna, if you wanna try to share your screen meanwhile while we are gathering people back in the room.
Let's see what you need to see. Oh. No. Can you hear me? And can you see my screen?
Yeah, perfect.
Great.
Just wait till you go in a couple of minutes when Jeff is back.
For sure.
Alrighty, I think we're going to go ahead and begin. There will be some people sitting down as we begin, but that's good. Anna, please go ahead.
Great, thank you. And I want to first thank everyone for allowing me to share some of my work that I've been doing over the last year. My name is Anna Pusak. I'm a second-year grad student at UC Berkeley, working with Jessica Liu, as well as some members of the Galactic Center Group at UCLA. I'm going to talk to you today about some of the trials and successes that we've had looking at the very crowded fields in the center of the Milky Way. My talk will be focused on two areas of my work. First part will be what I did the majority of last year was wrangling stage 1 data pipeline. Part of the process was looking at the data reduction of the DQ arrays, as well as parameter selection and examples of some weird up the ramp plots that I'll show you. Part 2 then will focus more on the Galactic Center itself, giving you a quick primer on the region and some of the pros and not cons, but areas for growth that we've encountered with the cycle 1 data we've been analyzing. Some quick observation specs. We're using the F170LP G235 filter grading combo with NearSpec in order to maximize our spectral resolution and radial velocity precision in this crowded region. Our data was taken in a 3x3 mosaic that was not dithered on the central 9 arcsecond or 0.36 parsecs around Sagittarius A star, the supermassive black hole. So the first part is this data reduction work, and here's a little cartoon of my attempts to work with the up the ramp data. Just kidding. So this is an example of some of the first data we reduced. When first reducing the data, we noticed there were certain patterns, including 3x3 boxes and 3x3 crosses that were masked, but that we weren't convinced needed to be masked. On the left here, you can see some DS9 captures of the different stage 0 and 1 data, including the DQ mask, where you can see one of these crosses quite clearly. On the right are the up the ramp data products from the uncalibrated in blue and the stage 1 ramp in red. The central pixel of this cross here, shown on the left and shown in the top set of plots on the right, is clearly something that should have been masked. It's flagged with everything under the sun in the DQ array: RC, hot, telegraph, dead, do not use, no sat check, other bad pixel. Clearly we didn't want to use it. You can see here how the uncalibrated ramps have a weird shape to them. But as an example of something that was unclear why it was masked is the top pixel of this cross, here shown on the bottom on the right, which had DQ arrays of jump detected, other bad pixel, and do not use. But as you can see, it's unclear why, because these ramps seem just fine. You could calculate a slope from these, and so it doesn't really seem like it needed to be masked. So we concluded that some of the DQ flags were being misassigned to pixels that otherwise had retrievable slopes. So in particular, most of the flags seem to be assigned during the dark step of the stage 1. I created a new dark mask that was built on the original, but if a pixel contained do not use and other bad pixel, we checked to see if the value of the dark current was outside of a range from -50 sigma on the low end to 500 sigma on the high end. And so if it was outside that range, it was still masked, but if it otherwise, we removed those do not use tags from the DQ mask array. And in the order of steps, you can see here I plugged in a new reference file, essentially, to work with in the flow. This alteration gave us back 85% of masked pixels, which is about 1% over all pixels, but since, as I'll get to, this very crowded region, this is no insignificant gain with understanding what we need. Here's a demonstration of that new pixel mask. The yellow with the red dots marked here on the left, those were ones that were outside the limits and so continue to be masked, as you can see on the right plot. And then the bluish pixels were ones that had been masked previously and so were regained with this new pixel masking. And as you can see, we gained back quite a few pixels via this method, even in this small section of a cube, or as a rate file. A lot of that work was resolved in May 2023 with the release of a new pipeline and PMAP for stage 1, but there was still some overmasking. As you can see in the progression of these numbers, pixels that had do not use were quite overmasked before the 1100 PMAPs. In that order of magnitude PMAP range. And we saw definite improvements with each subsequent PMAP release, but we still found some overmasking. And so we decided to use some stage 1 parameters that are described here. The saturation step kept down the saturation masking to just a single pixel instead of the 3x3 box of the default. And the jump detection needed a 3x3 snowball at least to be masked. And for most part, this seems to have resolved a lot of our problems, but there are still areas of confusion we have in the stage 1 data work. In particular, for example, we have several up the ramp diagrams that show slope recovery, but we're not really sure why. This is an example where the pipeline picked out a rate slope for the pixel, but the pixel saturates. It's not one that was part of the box across. You can also see it sits a little bit above where the groups are instead of sitting right on. So there's some sort of slope calculation here that's a little bit off. So for the most, we still are trying to understand more fully what the pipeline decides is a good pixel and what is not a good pixel and why for each. The second part of my talk has more to do with the analysis side of my work, in particular, how to choose a sky in such a crowded field. So first, a quick primer on the galactic center, because we've heard a lot of galaxies and planet talks, but I haven't heard a lot of star cluster talks, so it's kind of a different perspective. There is a supermassive black hole at the center of our galaxy, about 8 kiloparsecs from us, which seems to have some, it's called Sagittarius A star. It seems to have some inefficient accretion, despite a rich gas reservoir around it. It's also surrounded by a young stellar cluster, the YNC here marked in teal. That's about 3 to 4 million years old, where our near-spec data mosaic is concentrated, spanning 9 arcseconds around the supermassive black hole. This is in turn surrounded by a more extensive nuclear star cluster in yellow, which is captured by the accompanying NIRCam data that was taken with our Cycle 1 proposal. One of the big science questions that I'm working on is understanding the binary fraction in this region, which studies have indicated is lower than for the rest of the Milky Way disk, despite such a rich population of bright big stars, which you would think would have a high binary population. This is also the most metal-rich star cluster in the galaxy, as well as being heavily dust obscured. So near infrared observations are key for probing and understanding this region and in turn other galactic centers. Work done by Inbal Mizrahi at the UCLA enabled us to pull out sources within all of our pointings. And I want to point out a couple key features in this cube slice. First of all, notice how densely populated of a cube we're looking at. All of these red dots, it doesn't matter if you can read them or not, but these are all potential sources, cross-referenced from years and years of observation of this area. And so there's like well over 50 stars in each pointing. This is our central pointing right around the supermassive black hole, here marked in teal. And so it is the most crowded of all of our field of view, but it gives you a good sense of the kind of field, when I talk about crowded fields, what I'm talking about. I've also marked one of the most heavily studied stars here in orange. This is SO2, with a K magnitude of 14.1. And there's also another star of interest here in the pink, a 15.5 magnitude star. This is a star that has been tagged in an upcoming paper by Rui Yin that is a binary candidate in this region. And so obtaining near-spec radial velocities is critical for determining its binary nature and the binary nature of other stars that are too faint to see from ground. This data was also further processed with stage 2 using the IFU align and the EMSM weighting, as we heard, which mitigates some of the wiggles that I'll get into a little bit more detail. So to give some context, here is a ground-based spectra from Keck's AO system OSIRIS. Because SO2 is such a well-studied star, it acts as a good baseline to test our analyses. I want to point out a couple key features of this spectra. First, there's a deep hydrogen absorption line that helps with calculating radial velocities. The wobbles here on the left are from some issues modeling out the telluric absorption. As we know, the atmosphere is the bane of every ground-based observation. You can see these other data points are probably residuals from subtracting the sky, which you can see here, the sky flux in blue, as well as the residuals from the model applied using the spectrofitting package StarKit. So to compare that with JWST, you can see here still in the red, the OSIRIS data offset from the JWST data, but right away you can see the wider wavelength range that we get with JWST. And this is what makes studying this region so important with JWST, because it gives us more lines to work with when it comes to calculating radial velocities, as well as to do spectral typing of a lot of these stars. It can also see deeper than ground-based observations can. The gap here is due to the physical gap between the two detectors in NearSpec, and these gray vertical lines indicate sky lines that may have been over-subtracted in the JWST data when we were choosing that sky. To give you a little bit closer look at that, you can see at these insets, these are areas where the two instruments overlap and the different information that's there. But we can also see lines maybe that we can't see from the ground, which you can see on the left. Here we have more H1 lines, as well as details about how OSIRIS, the actual spectral resolution difference between the two. These sky lines that are marked in the gray are a problem we are still working on. You can see here on the left, the model doesn't reach the same depth as the data, and we think this is due to sky selection that is over-subtracting from our data. This is the biggest hurdle we've had is how to choose our sky to subtract. Here are two examples that we've tried on a 15.5 magnitude binary candidate that I pointed out earlier. First, notice how close the star is to another bright star, and an even brighter one. This is actually a Wolf-Rayet star up here. We've had to take an aperture here marked in red around the star due to the undersampling issue we've heard about earlier today. And I'll get to a little bit more about that on the next slide. The plot on the left shows an example where we take the median from a patch of sky nearby. This is that light blue circle there. And the plot on the right shows where we took an annulus around the star, the light blue ring. In general, one of the biggest issues we had when we look at the sky spectra is we see stellar features, which indicate that these sky regions are not so much background, we're not really subtracting background, as much as we're subtracting unresolved stars. So there's even more out here that is not necessarily being seen as full sources. There's always more stars to find in the galactic center. And so how much to subtract then becomes confusing because we may be over-subtracting the flux of the target of interest. Okay, so back to these two sky apertures. Both have pros and cons that are clearly seen here. The nearby patch, which is the blue spectrum, has significantly lower errors. It's just this like slight light blue around the darker royal blue spectral lines. And most of the errors in our modeling come from the sky, and so that really affects how we can model the star using StarKit. The annulus, then you can see the gold and orange seems to remove a lot more of the contaminating light like you see here, but has huge error bars. So it also, here's that wiggle pattern we saw a lot earlier. I'm very excited to try some of the solutions that have been mentioned today. And we think, like it's been said, that this is due to undersampling the star, or even undersampling the star next to it. As you can see, it's taking some here, but not the whole spaxel range. And so it's producing this wiggle pattern in the resulting spectra. Like I said, there have been some great suggestions over the past 2 days that we're hoping we'll be able to help to explore, but so far we can't get rid of these wiggles using polynomial fits, or I haven't been able to do sinusoidal fits either. So what we've done is just to have those to collectively count up several spaxels and iteratively average them to get the spectra. And so my quick summary, overmasking of pixels from early on seems mostly resolved, but still needs to adjust pipeline to get more pixels. We have uncertainties in how the ramps are calculated for certain pixels where we don't necessarily think the slope should be calculated. The galactic center is a rich region that needs a lot of considerations that aren't necessarily accommodated in the current reduction analysis. But there's a great potential for a variety of science and exploration to complement and expand on ground-based observations. And so finally, the sky subtraction is one of our biggest roadblocks, and hopefully I can hear some solutions. So that's all I have for you, and thank you.
Awesome, thank you very much. Jane is going to get mic'd up, that's good. First, I just want to make a comment. You've done an excellent job of making me feel like JWST doesn't have enough Angular resolution. That I've never felt it's been so poor as looking at your images. So congratulations on that. There are a few comments in there now. One of them, a couple of us speculate that the slope, the ramp, the integration you showed that had the two different slopes has a neighboring pixel that's saturated halfway through that particular integration, and the charge is starting to spill. So it would be good to check that. If that's not the case, then I would love to hear about it, because we should figure out what's going on then. But that's our theory.
Yeah, I can double check.
Yeah. Are you also exploring PSF fitting, not just the aperture photometry?
Not actively, but we have talked about it.
Yeah.
So it is something to consider. And I've been slacking with Imbal, who I mentioned a bunch, and we're like, oh, all these things that we can try.
Yeah.
So, yeah.
Yep. Yeah, that seems to be something people are doing. Anyway, thank you very much for your talk. Next up, we have Jane Morrison. Thank you, everybody, for your comments in Slack. They're super helpful.
Okay, today I'm going to talk about creating spectral cubes with the MSA in a slit-lit stepping mode. And I'll explain slit-lit stepping if you don't know what it is. And the talk after mine. No, I do. Now my light screen. Thank you. Thanks, Mike. The talk after mine is also on slit-lit stepping. So everybody should know the power of slit-lit stepping after today. This is work I'm doing with the Garden team, and the core group is listed here on this slide. I have there's two students that I want to point out, Celia McCahey and Ezra Zuka. Raise your hands because you've done so much work. I'm going to show some at the very end. I mean, you look so good. They're going to be like, they might be ruling this place one day. They're so good. They're so good. And Susan Casson is a PI on this project, and then Cami Pacifica is the co-PI, and I'm sorry if I slaughtered that last. The reason I'm up here talking about this is that I'm going to talk about the software that was developed specifically for MSA slit-lit stepping. I should say that I work on the JWST pipeline, and myself and David Law, we wrote the cube building step for IFU data. And so we took a lot of the components that were in the cube building step, and we used them to make this MSA slit-lit stepping. So that is how I got involved in this project. Said it was going to work. Do we just push it? Okay. All right. That works. Okay. As an earlier talk, I wanted to show you the MSA. I want to point out here, because the MSA is, there's a lot of shutters that you can open and close, and the slit-lit stepping technique takes advantage of the numbers of shutters that you can open and close. So, let's see, this should work. Kind of. Oh, there we go. Okay, so there's 365 each quadrant, so there's 4 quadrants. And all of, you can't really see the resolution, but these are all little shutters. So there's 365 shutters by 171 shutters. And then the field of view here, I want to point out, of all of the quadrants is, it's a 3.6 arc minutes by 3.4. So we've got a fairly big area of the sky when you're looking at very, very faint regions. So before I talk about slit-lit stepping, I just want to remind everybody, because if you don't use the MSA much, maybe you're like, well, you know, how is this different than normal operation? And in normal operation, there's 2 ways that typically an MSA observation is set up. You can either do a nod, where you you have, so these are not positions where you have three different, you would put the source at three different locations in a slitlet. So let me just say one thing. One of these is a shutter, and a shutter has 2 by 4 pixels in it. And when you put more than one shutter in a row, then you get what's called a slitlet. And so that's when I talk about slitlets, I mean a number of shutters in a line. And so there's the nod strategy, and there's also dithering strategy over here, where you just dither around, and again, you have your slitlets that you dither. And in both cases, the pipeline will take the data, and it's going to give you a fully calibrated, distortion-corrected data in a virtual slit frame. And then from that, you get your extracted spectra. And I'm going to show you the difference when we do this slits. Goodness. Okay. All right. So slitlet stepping is, okay, it's super cool. So I hope I can do justification of this. I got involved in the project really after they had come up with this, and they had come up with this incredible strategy of how to observe many galaxies at the same time. So what happens is we're gonna have a slitlet. So let's just take this A object with galaxy here. So we've got 5 slitlets in a row for this object. Then over in this one over here, we have 4 slitlets in a row. And in this smaller galaxy, we have 2 slitlets in a row. And so that's that first observation. And then you're going to slitlet step. So you're going to step over one in the next observation. And you're going to take this next step right here. And then each of these objects, you're going to get 6 steps. This is how this program was set up. You don't have to do 6, but this is how this program was set up. So you're going to have 6 different slitlet steppings. But the cool thing is, if your galaxy is large, you can do 6 separate steps. Or if it's a little smaller, like this one right here, you cannot move. You don't have to move to the next group of slits. You just stay here and you do 2 steps here, and then you do a step and a step and then 2 steps at the end. And you're getting some of these smaller and fainter guys, you're getting more observations on them. And then if you're a really little guy, like this one right here, you can get, which I'm having trouble with, there you go. You can do, you do 3 steps here, so 3 observations here and 3 observations here. So you can really play with the size of your galaxy and the depth that you're gonna observe, because you're gonna observe all of these at the same time. You're gonna take your MSA, you're gonna configure, you're gonna find your objects, you're gonna open all these different slits, and then you're gonna observe them all at the same time. And so that's what's really cool about this is you're turning the MSA into a multi-object IFU. And that's super cool. I did it. Okay. So, like I said, turns it into a multi-object IFU. And the reason this is like you take the MSA, it's got all these slits that you can open up all over the place. We've got, you're taking that aspect and also the aspect that we're going to use a high resolution grading. So for all these observations, we used the G235H. And so you're able to configure the MSA so you can get multiple galaxies observed at the same time. And you're going to use a very high resolution grading. And so with this program, we observed, we were able to get 56 galaxies in 74 hours. And if you try to do that with an IFU, it would take like 4 months of observing time. So that's why this is such a cool way to operate. It's so efficient for the telescope. Few things about this. This is this isn't a, you know, a official mode. Like, we've done this, and the group afterwards, after my talk, is also going to talk it. So there are people that are doing this, but there's just a few things in the pipeline that you have to be aware of. You can run cow detector 1, same as everything. Then one of the tricky things, the first thing that we had encountered was if you have MSA data, you have an MSA metadata file, and that's sort of like your Bible. That tells you, here's all your observations. It tells you the sources, their RA and DEC, and where they're located in each file. So that is what the pipeline is going to use to pull out all the different slits and know how to associate them together. But because we did slitlet stepping, the program that sets up the MSA file, it has a smaller tolerance. So it says your RA and DEC is here, but we stepped off of it, so it thinks we're in a background. So the first thing we had to do was a lot of the sources in the MSA file were flagged as backgrounds, negative values. So the first thing we had to do is we had to go in there and clean that all up. Because that's our Bible. That's how we know how things are associated with each other. The next thing is, well, we kind of did this. We built some cubes, realized there's, like, everyone is like, not everyone, but a lot of people have said, there's, you know, bad pixels are contaminating your data. So we needed to go through and flag extra additional bad pixels. David had developed a tool to do this for the IFU. He adapted that tool, and that's what we're using right now for the MSA, and it's doing a pretty darn good job in flagging the bad pixels that contaminate our cubes that we make. CalSpec 2, this is an area that we will come back to after we've done more work, but right now we're turning off the bar shadow because we've got these really long slitlets. One of our slitlets has 14 shutters put together, and that kind of gives some haywire to the pipeline. Bar shadow currently, I think there's a PR in for it to make it work for these really long slitlets, so that will soon be in there. The path loss correction we've heard today, we've heard different people talk, and listening to Anna's talk earlier, I'm going to go and grab her stuff off GitHub and play around with that and see if I can improve the path loss correction. But there's just some areas that we know that we're going to have to spend more time with. But right now, let's just use the pipelines pretty much as it is. We did turn off bar shadow. We still have the path loss correction on. And right now, we're stopping at CalSpec 2. We use the data from CalSpec 2 to make our cubes. The first thing that you do in making a cube is you've got to find how big of an area on the sky it's going to cover. So we take each slit. This is step 1. You take each slit, map it to the sky, because we're going to build build a cube on the sky. So I just wanted to kind of show the process of this. Here's the first one. This is just building up, because if I showed the last one, this looks confusing, that's just a bunch of lines. So this is one slit mapped. This is actually 4 slits mapped up, because some of them, we've got NRS1 and NRS2 here. This is 10 slits mapped, and this is when we have the full 30 slits mapped up to the sky. So that is our footprint on the sky spatially of what we're going to build. And which one of these buttons works? There we go. This is how we're building the cubes for the MSA. We're simply we have 3 steps, and we use a lot of stuff from the IFU cube building code, which made it easier. So here is a slit. We've mapped all the slits that we've grabbed them all, and we know how they're associated together. We map it up to the sky. We know how big it is. We know how big it is with the wavelength dimension too. So this is my representation of what it looks like on the sky. Not the best, but you get the idea. So this is my MSA cube on the sky, and then we go back, and it's a drizzle technique just like we do in the IFU. And we just take a pixel over here, and we use the data models. We use the near spec transforms and the WCS And just like we do in the IFU mapping, we take a pixel corner and we map it to the final cube, keeping track of the spatial coordinates and the wavelength. And then when we plop this guy, we take, this is in the spatial and the wavelength information for 1 pixel. We plop it over here. We keep track of the overlap that 1 pixel does with all the voxels in the cube. And in fact, I just recently changed so it uses the exact, it calls the same code that the IFU cube building code uses. It's a C extension, and it uses that, so it's pretty darn fast. Then you've got your spectral cube done. And I wanted to show just some quick examples that Celia and Ezra made for me. And so we've got we've got an image of a galaxy. This one's bear claw. They had some ones they really liked. This is bear claw. The center is the IFU cube, and you're going to see that I'm going to play it, and it's going to go through the wavelength planes of the IFU cube. And then there's the extracted spectra, kind of going off the side of the screen there. And there's a red line. You can actually see it better. Oh, it's a very faint red line. Okay, there's a faint red line. Oops. Here we go. There's the red line right there. This is the wavelength plane that it's on, and you're going to see it go through the different wavelength planes. And the really interesting thing is not only do we get an extracted spectra, but if you will look, as this moves through the different planes, you're going to see these features, these arms. You're going to see how we can get the velocity of like the different locations of the arm. So that's the really cool thing about this. So let me, nope, I don't know how to do this on here. How do I go back? Little technical difficulties. I should have, there it is. Okay, sorry, there. Hopefully I click a button. There we go. Okay. So I would stop it, but it's going to be too complicated with this thing. But if you can just see the features, that's the, I know it's a little fast, but if you can look between the two, you can see how the different features are moving, and you can see how the wavelength plane, it first went through H alpha and then into, and where is it now? I don't see the red line from this angle. Oh, we're at the end. Okay, so I'm going to show this again, because I showed that too quick. So you can see H alpha, and if you really look, you can see how you can start to see some of these arms, whatever, these. You can see these arms moving in there. So let me, okay, well, there we go. Now I'm on the coffee pot. We're just going to have to do it for coffee pot. I'm having some technical difficulties up here. There we go. So in the it's the same thing. It's moving through, and you can see the features of the different lines, and you're able to, if you correlate between watching the two of them, you can see how different different regions. We can look from these, and we can see how the different regions are rotating. So that's the cool little added feature of having a spectral cube. And I think I'm going to stop it there. Okay.
Awesome, thank you so much. I think we're just going to move on to the next talk at this point, so if we could get mic'd up for the next talk, which is remote, is that right? Yeah, okay, so that'll be good.
You can grab the screen.
Hello. Can you confirm, one second. Can you confirm that you're seeing the screen and that can also hear me?
Both are great. You're clear to proceed.
Okay, thank you so much. Starting the clock on my end too. So hello everybody, my name is Ivana Baric and I am currently a postdoc at UC Davis, working with Tucker Jones, building on what Jane has just talked about. I'm going to proceed and continue talking about the power of the MSA slit stepping and demonstrate yet again how we can achieve high resolution pseudo IFU observations in a time efficient manner. I have been leading the effort in the data reduction for the program titled GEO 2136, the PI of which is Tucker Jones. And just to give a background to begin with, this is the first program that provides the resolved kiloparsec scale 3D spectra spanning the epoch when first modern thin disk galaxies emerge. And just to give a background, the reason why this is relevant can be illustrated in this simple figure taken from Wisniewski et al. 2019, where we see that the degree of rotational support in galaxies varies as a function of redshift and also stellar mass, where galaxies at higher redshift, so larger than 2 and 3, show high degrees of dispersion-dominated support, meaning very likely thick disks or non-disk structures, and moving to the lower redshifts, we're seeing rotationally supported systems. And so the question that remains is what actually drives this transition from galaxy populations, from irregular clump structures to thin disks? What is the role of accretion and feedback in driving this transition? And redshift around when thin disks first emerge, so it would be around redshift 1, would be the crucial is the crucial epoch for us to try and address these questions. Historically speaking, one way or the best way to shed light on this type of question is through reliable kinematic data, and this has been done with an IFU, hence the motivation to gather pseudo IFU spatial and spectrally resolved data. We're focusing on redshift 1, targeting rest frame optical diagnostics, and we're targeting galaxies scattered around the main sequence, 43 of them drawn from the EGS field. Now, to keep the science objectives in mind here, what we're trying to reach in order to be able to identify thin disk structures, you need to be able to reach intrinsic velocity dispersions lower than 30 kilometers per second, meaning we require H alpha signal to noise ratio to be around 5 at a certain radius. And in order to achieve this, of course, you could use an IFU, and here is just an example of a target galaxy. Only projected on it on the left side is the IFU aperture, or how much we would, what is the surface area that we could get with an IFU. Keeping this objective in mind, and using, if you were to use an IFU that's on board James Webb, you would need to integrate for about 8 hours per each source in order to reach this sensitivity. And given the number of galaxies that we are talking about here, this quickly goes north of 350 hours of total science time, and this is without overheads included. In the meantime, just like Jane has said in the previous talk, if you just consider using MOSMO to perform the same task, it becomes abundantly clear that with the multiplexing ability, the time efficiency improves more than 15 times, where in 20 hours you can do you can achieve the exact same type of product in the end. So with 20 hours of integration of total, this translates to translates to approximate time efficiency of about 30 minutes on source, which is a stunning improvement in comparison. Imperative here is to achieve uniform coverage of the target in question. What you're seeing here is an example of a number of slits that we are using to form a slit for this particular target. So as Jane has mentioned in the previous talk, you can in the MOS mode you can choose arbitrarily the number of slits that you will form your aperture based on for your targets. And wherever possible, we open 5 slitlets, which is our maximum that we want to go with. However, in certain cases, we're forced to go with 4 or even 3 slitlets in rare, three slits to form a slit in rare occasions. In order to achieve the uniform coverage, it's important to have a appropriate observing pattern. And for this reason, we chose something that looks like illustration on the left, which is following a typewriter structure, where we step 9 times in the dispersion direction by the width of the slit, so 0.2 arc seconds, and we also dither in the cross dispersion direction by the width of the bar shadow, which is 0.075 arc seconds. Stepping 7 times by the bar shadow width, we ensure that we have the uniform coverage for each spaxel in a slit, achieving in the end about 2 hours of integration per each spaxel and achieving the signal to noise ratio that is required for our objective. As has been pointed out in the previous talk, this is a largely unsupported mode at the moment by the standard pipeline, which requires us, in order to do the optimal data reduction, to first of all customize the existing pipeline to fit our needs, and also to build the data cubes for this particular pattern. We have developed an independent class in order to design the cubes out of the 63 exposures that we have per each target. What I've given here is 4 large steps that we take in order to bring us to the final cube that is designed. What I'm going to do in the following slides is just give a high-level overview of these steps that we needed to take, and also challenges that we faced on the way to design the cubes, and also give an overview of which challenges still remain. So starting with stage 1 and pre-processing, at least up until a few months ago, I'm not sure if this has been, if the default values have been permanently changed in the standard pipeline in the recent month or so, but it has been obvious that using the default parameters in stage 1 of the standard pipeline of the jump step results in a number of artifacts, which we have seen over the last day and a half even in other modes. So with the assistance from help desk and also experimentation on our end, we have converged to a subset of non-default parameter values, which combined in jump step give us a snowball-free slope image. However, what remained at that stage then was a remaining 1/f noise, which, like a number of other teams, we have decided to use the NSClean from Bernard Rauscher in order to achieve this additional 1/f noise correction. And using these slope images, we moved on to the next step, which is the custom stage 2 and 3 combined pipeline. Now, given that MOS mode, like every other mode, in the standard pipeline contains a number of steps. We decide to reduce the number of steps that are taken in the standard reduction to its bare minimum, only reducing our use to the World Coordinate System or WCS assignment, flux calibration, bar shadow correction, resampling step, and the 2D spectrum extraction. What we also need to include, but we were unable to apply, at least from the standard pipeline, is path loss correction and also master background subtraction, because these particular steps are not functional at the moment in the standard pipeline for a non-characteristic or non-standard choice of the number of slits in the slit level or in the aperture. So anything other than 3 or anything larger than 3, path loss correction, master background subtraction is not going to work. To mitigate this, in the following weeks, we are implementing the sort of a manual version of path loss correction, which is about to come, or which is going to be implemented at the end of stage 3, where at the output or for the output 2D spectra, we will use the path loss model for the uniformly illuminated slit to just perform the path loss correction. And also learning today from Anna de Graaf's talk with the code that she has developed, so to see from which one we get better results. Master background subtraction remains an open issue, but there is something that so this is something we still need to work on and is not included yet in the current cubes that we have produced. But something that I want to point out is the experiment that we actually did with the targets on which we were forced to have 3 slitlets on. So because we have 3 slits on those targets, standard path loss and master background works, so we can actually see the effects. And from here, the topmost panel shows the 2D spectrum that doesn't have master background and path loss applied to it. Middle one has the in the processing include the standard pipelines, path loss, and master background subtraction, and the bottom plot is then the difference between the two. At least now, what we see from the performance of the standard pipeline regarding this particular issue is that while master background subtraction offers or seems to offer marginal improvement as compared to when it's not employed at all, it seems that the bigger issue is introduced with the fact that the actual signal is being subtracted, which you can see in the bottom panel, which is something we definitely want to avoid for our science objectives. And so now the question that reopens, or the next question that opens, is whether the standard pipeline's master background and path loss correction step even works as expected in the first place, or if it does, then I guess we can ask ourselves whether the when we're using a high resolution grading and filter combination, how necessary it is to do the master background subtraction. Obviously, this is something that we need to continue testing and implement a manual version of or our own solution to this problem. Moving on with the 2D spectrum, this is an example 2D spectrum of one of the 63 exposures of a single target that doesn't have the master background correction applied to it. You see that some of the outliers still remain in the 2D spectrum, which haven't been caught by the stage 1 processing. And this means that even though we run stage 3, which does have the outlier detection step included, it doesn't, or at least up until last month, it hasn't been working as intended. So our workaround in this case was to use Peter van Dokkum's LA Cosmic algorithm which seems to work reasonably well, except for on the edges or more noisier regions. However, some improvement, at least for us at this point, is better than no improvement at all, because these 2D spectra need to be used in order to combine them into the cube in the end. This brings me to the cube design, and for the sake of this talk, I'm going to just briefly say that the combination of exposures in the dispersion direction is rather trivial because of the stepping by the slit width, and the non-trivial combination of exposures is in the cross dispersion direction, which is reduced to sort of Nyquist oversampling onto the common grid. And to treat the remaining artifacts, like the hot pixels that we have seen on the previous slide, we circumvent this issue by taking a median along cross dispersion direction, which seems to be working well for the time being, but we will be replacing this as better solutions surface. Here you can see the color image of the example galaxy I've showed at the beginning of the talk, and right next to it is a cutout from the produced cube that comes out of our pipeline from one particular spaxel. You can see what the actual spectrum, extracted 1D spectrum, looks like. And finally, based on H alpha, we have reconstructed or constructed the velocity map. These two plots provided by the PhD candidate at UC Davis, Chris Mortensen. Last but not least, or at least in the last couple of seconds, I just want to point out one issue that we have encountered in our processing. So since we have so many 2D spectra for our target, so each target has 63 exposures, so 63 2D spectra, it was, I guess, inevitable to see any of the weird effects that might have been inevitable to rise. So what we see is that some of the exposures for our targets are affected what seems to be the circular patterns, and it's brought to our attention that this is something called alternating column noise, and as of October, this is marked as the known existing issue. However, what we have noticed is that this particular this effect is typically tied to NRS2, so almost exclusively is tied to the NRS2 detector, and also it's not consistent across all exposures. So it's not that this particular exposure is going to have all of targets affected in NRS2. So it seems to be rather random, and it's something that we, and I'm assuming Space Telescope is also working on resolving, but I wanted to bring this to your attention or strike a discussion. Thank you.
Awesome, thank you very much. So there's some people typing. While they're typing, I'm going to ask, yeah, go ahead and get ready. Do we have any targets where we have both types of data? Has anybody done an IFU observation in the fields where you've tried slit stepping?
That is a good question. Not sure at the moment. So I know that what we are targeting is the EGS field, and we were looking whether there is an overlap with Sears program. Although they're not doing the IFU, they have been doing their own observations with NearSpec, but we don't have any galaxies that are overlapping with theirs. So that is regarding just generally any other NearSpec observations in the EGS field. But it will be interesting to see whether anybody has done IFU actually.
Yeah, because I paid close attention when you said it yields the similar quality data, but if we're going to go down this path, we really want to make sure, right, that there's not some funny thing. So I think there's going to be some discussion about the last issue you were mentioning in Slack, but we're going to leave it there, and we're going to move on to the next speaker. Thank you very much.
Thank you.
Okay, great, thank you. Hi, I'm Elle Bogat, pronouns they, them. I am a graduate student at the University of Maryland / NASA Goddard. And I'm excited to talk to y'all a little bit of a topic shift about SpaceClip, which is a data reduction pipeline for JWST high contrast imaging. And shout out to Aaron Carter for the slide design. I hope y'all aren't tired of yellow hexagons. But I would like to preface this talk with a caveat that I am not actually a developer of SpaceClip. I am giving this talk on behalf of the developers, many of which are based here at the Institute. Jens Kammerer, Marshall Perrin are based here, and Aaron Carter and Jaron Leisenring are at Arizona and Santa Cruz. I swapped the order. But so they are the heavy hitters with this project. There's a huge team of people supporting them, and a lot of really great work has been done to enable some really cool high contrast imaging stuff. So I want to motivate the science a little bit first with just some snapshots of beautiful images of dim things orbiting bright things that have been published in the past year or so. Notably, this image on the left is the HR 8799 system, which is a system of 4 super Jupiters. And so you can see little PSFs from each of those 4 planets, and pretty much all of the light from the central star has been suppressed and removed, so we can actually see these dim things and do really cool science. There's also a UMIC edge on disk. Very pretty, big fan. All right, so the modes that we're going to be working with are the NIRCam and MIRI coronography modes. And the main thing that differentiates the coronography modes from just the standard imaging is the use of coronagraphs. So this is a mask that you'll place in your optical path to suppress light in the center of your field of view. There are a few different techniques to do this, and we have a lot of steps to go through to get from our raw data to our science-ready product. So that's what I'm going to talk about. I think by now we're fairly familiar with what many of these artifacts and residual things are. There are a lot of sources of signal that are not necessarily the astrophysical signal that you're interested in. There are also sources of signal that are not physical really in the sky at all. Some of the aggressive saturation correction that Anna mentioned earlier. We get residuals if your dark files are not as clean as you would like them to be. And then, of course, there's the neutral density squares that are patches of additional attenuation in the coronagraph filter that we use for target acquisition of bright objects. And then you might have background sources that you're not particularly interested in, this being the NIRCam example. And we have analogous sources for MIRI. All of these things need to be mitigated and removed so that we can do our science. And so this is the overall structure of the pipeline. The first 2 of these phases sort of correspond to the detector 1 pipeline and the image 2 pipeline from the JWST official pipeline. And so these are going to be used across all of the imaging modes. However, high contrast imaging, because of these coronagraphs, we have some extra fancy steps we need to do at the end. And not all of those steps are included in the official JWST pipeline. So in terms of what SpaceClip itself is, it's an end-to-end reduction pipeline for JWST, NIRCam, and MIRI coronography. It wraps the official JWST pipeline, and it also interfaces with the PyClip package led by Jason Wong for PSF subtraction of your central star, and it also interfaces with the Web PSF package developed by Jaron Leisenring, among others, to model and simulate JWST data. So this is an open source package available on GitHub. There is a QR code for your perusing pleasure. And yeah, generally we're wrapping and building off of the official JWST pipeline with some extra steps at the end to get us from our data to publication-ready plots. And so another way we can break this down is we can talk about what parts of this pipeline are already provided by JWST, and which ones we replace versus which ones we are sort of making up on our own. And so we really rely heavily on the first two stages of the pipeline. But for the PSF subtraction phase, we're going to, and by we, I mean the developers, I just want to make that clear, but we'll provide our own PSF subtraction through PyClip, and then the last two stages I mentioned are coming out of nowhere. Not nowhere, but not from the official pipeline. So to talk about the ramp step a little bit in more detail, the main things we're going to do are call the JWST detector pipeline step with some modifications. One of the major ones is that we're actually going to completely skip dark current subtraction for NearCam. And we found that this helps because the current dark current subtraction sort of introduces more residuals than it removes in the form of these sort of dark blue patches where we're seeing over subtraction from those dark current files. Then another thing we have to do is overwrite the reference pixel correction a little bit, because coronography mode involves just using a subarray of the NearCam detector. NearCam is going to be my example for most of this talk. We don't actually have access to those reference pixels that are along the edges. And so we're just going to override and tell the pipeline, hey, these are the actual pixels we want you to use. And so we'll select the 2 or 4 pixels along each edge and just say, hey, please use these instead. This can result in some over subtraction if you have something particularly bright on the edge of your field of view, but overall it works pretty well. And then we're also going to implement some 1/f noise mitigation. This is a routine that Jaron Leisenring merged into SpaceClip just a few weeks ago, so it's hot off the presses, in an effort to recreate as close to what Bernie Rauscher talked about yesterday, but in a more quick and dirty fashion, so it's not quite as computationally intensive, where we look at all of our frames in an integration and subtract the average of all the frames from each individual frame. So the residuals you're left with are dominated by the 1/f noise, and then we'll model that and subtract it from the original data. And that seems to work fairly well for our current intents and purposes. If we move on to the stage 2 step, we're going to do the same thing where we're sort of wrapping the stage 2 pipeline. And then we are adding some additional steps after this for NearCam, that is median subtraction via determining the median with sigma clipping and then subtracting that on a frame-by-frame basis. And similarly doing background subtraction for MIRI. Then we have some additional outlier identification based on temporal and spatial variation, so we can pass a median filter sort of over the detector and look for spikes. With all of these have like thresholds that you can tune to your preferences. And you can also pass a custom mask to flag any bad pixels that the pipeline may have missed. Because the coronography detectors are just 320 by 320 pixels, this isn't like a huge, it's not an impossible task to just go through and clean up a few extra bad pixels. Certainly not ideal, and I'm really interested in the stuff that everyone else is doing for outlier flagging, so we can fully automate that. And then the last thing we have to do is carefully realign and recenter the coronagraph to the center of the field of view, so that when we are trying to remove the rest of this big red splotch, that's pretty much all starlight. There is a planet in there, I promise. We'll see it later. But we still have a lot to remove, and so we have to make sure that not only are those PSFs stacked on top of each other correctly, but also via modeling, we have to know exactly where the star is positioned behind the coronagraph. And so we'll do this with some forward modeling using WebPSF to determine the exact position of the star. We'll get everything aligned so that we can feed it into the PSF subtraction step. And so there are a couple of different methods for PSF subtraction that we can use. Typically, your planet flux is going to be vastly outshined by the star. And so if you take an additional observation of the same system after rotating the telescope, then your PSF of the star will rotate with the detector, but the planet will stay fixed on the sky. So that is one method to subtract the stellar PSF. The other option is to observe a spectrally similar star and model the stellar PSF and then subtract it from your image. So with PyClip, we can do one or both of these methods. Clip referencing the Karhunen-Love transform, which allows you to build, it's some linear algebra trickery that allows you to build a model of an image based on like orthogonal situations that I personally don't understand very well, but someone else does, so it's fine. And this allows us to successfully remove the starlight while maintaining, like actually tracking the knowledge of specifically where the star is in the background, which is a major thing that we do not get through the masked stage 3 product. We lose, when you download the stage 3 product just for mask, you lose the information of where exactly that star is, so you can't get as accurate astrometry. And you also lose the information of what you did in your algorithm with your rotating and your subtracting, because that is going to significantly affect the actual like flux counts in these pixels, which will prevent you from getting very robust photometric measurements. To illustrate this, we have a near-cam observation and a MIRI observation of the same system using angular. So on the left is our unsubtracted starlight from the Callens files. Then we have the angular differential imaging, so just from the rotation. Then we have reference differential imaging, where we're not doing any of the rotation, but we are subtracting the stellar PSF model from a reference observation. And then a combination where we get to combine both methods at once. And you can see that for the same observation and the same filter, you can end up with different amounts of flux appearing to come through because of self-subtraction. And so if you don't know exactly what you did in that algorithm, it's very difficult to understand the actual astrophysical flux of this object. So this is where our next steps are going to come through, and why it's really important to know exactly what you did in that first step. So the concept of the contrast curve is essentially a measure of the sensitivity of your observation as a function of separation from the target star. So this is a 5 sigma contrast curve where the units are just flux contrast. How much brighter is the star than the image, than the object that you're trying to observe? And so if your object, such as HIP 65426b, lies above that curve, then it will be detectable over a 5 sigma confidence. And if it's below that curve, it will be undetectable. And so as we compute these contrast curves basically by injecting false planet signals into the Callens data and then applying the exact same algorithm we used to subtract the PSF, measuring the resulting flux of the planet at the end of that process. That allows us to understand what is our actual sensitivity in all these different regions of the field of view. And you can do this with multiple reduction pipelines, so it actually is a really useful diagnostic tool to test, hey, what is the best method to use to observe an object at this separation around this star. Finally, we are going to use that same sort of forward modeling technique to actually fit any companions that we see. And so here we're seeing on the left is the data in the NIRCam and the MIRI observations, the model that has been forward modeled and passed through the same reduction pipeline, and then the residuals at the end, and you can see that we're able to fit them fairly well. And so it's these contrast curve capability and the companion fitting capability that aren't involved in the JWST pipeline, but really rely on clear knowledge of what you did in your reduction process to be able to back this stuff out. So with that, this is very much a living code It is actively in development, and we're really interested in ways that it can be improved. I know outlier correction and 1/f noise are really big topics that we can still absolutely improve on. And that is all that I have. Thank you very much.
Awesome, thank you. Could you go back to the contrast curves?
Yes.
So one question is, why does the contrast curve for the F1140C look like it's barely detectable, but the image, it looks very clear?
So this line represents a 5 sigma source, which is going to appear very clearly. Technically, like if the object showed up slightly below that line, maybe it would appear as 4 sigma, and you would still technically be able to see it. It might not be as like scientifically robust.
Got it. And if you'd go forward again, I think it is to the snake logo.
Yes.
Excellent snake logo. That's one of the comments.
I will pass that on.
Yeah. A longer question, which I think may be better to answer, but just to say it out loud, from your perspective, what parts of SpaceClip should be added to the standard pipeline, particularly for hands-off generation of products in MAST?
I think that a lot of the stuff that we're doing in the stage 1 and stage 2 steps could be easily integrated into the JWST pipeline. I think another thing that would help is tracking the precise location of the center of the coronagraph, and the location of the target star will help a lot for being able to get quicker astrometry.
Is that something that's measured along the way, and you're saying just keep that metadata?
It should be. I don't know if it is officially.
Could be.
Yeah.
Okay, good. Yep. What else? Keep going. Sorry.
I think those are at least the most feasible ones that I can think of. I'm not sure how we would be able to keep track of all of the algorithm subtraction and whatnot, but I am interested in discussion about it.
Perfect. Thank you so much.
Thank you.
All right. Hi, everyone. I'm Taylor Bell, and I have the pleasure of having been invited here to talk to you about the Eureka analysis pipeline, which is also an end-to-end pipeline, but instead for time series observations. So one of the key motivations behind developing the Eureka pipeline is that programming skills shouldn't drive scientific success. It's great that some or many of us might have good programming skills, but that shouldn't be a prerequisite to being able to do excellent exoplanet science. However, reducing JWST time series observations at present requires some substantial customized software that's not currently provided by the JWST software package. Based on past experiences with similar experiences with Hubble and Hubble and Spitzer, custom pipelines are seldom open source and well-documented and user-friendly. My own code is a clear example of this. I previously wrote a Spitzer analysis pipeline, which was open source, kind of documented, but not very user-friendly. And so kind of from having experience trying to develop that and understand just how hard it is, I don't judge anyone for failing to meet all 3 of these. It's a great deal of work, and ideally something that would be approached by an entire community to share resources. Oftentimes these custom pipelines lack documentation, testing, intercomparison with other pipelines, and general user supports, or they're closed source. And so this kind of creates a members-only environment where newcomers to the field either have to know someone who knows someone that can give them access to the pipeline, or know someone who knows someone that can teach them how to use the open source pipeline. So the project philosophy was to create a community-supported open source pipeline that's modular in design and easy for anyone to use. These are the main contributors to the Eureka pipeline so far. It is an open source and pipeline, and anyone is encouraged to submit their own edits if they want to. But so far, it's been a development team of about 12-ish people that have contributed so far. And we published a paper in the Journal of Open Source Software in 2022 outlining the general flow structure of the Eureka pipeline. We follow a similar stage naming numbering scheme as used by the JWST pipeline, stage 1, stage 2, except we extend it all the way out to stage 6 to go all the way from raw data to planetary spectra. Each stage of the Eureka pipeline has as an input a Eureka control file. These are similar to the YAML files and may at some point be replaced by YAML files, which specify key processing values as well as methods. These ECFs are copied to the output folder to ensure easy reproducibility of your analyses. So if someone says like, hey, can I try and use your code on a different planet? You can just give them the ECFs. If they run it on the same data, they should get the exact same results. And that makes it really easy to transition to a new target and like get at least a decent first analysis. And then you can tweak things as needed if you need more or less background subtraction, things like that. All of the parameters in ECFs are documented in the templates that we've made for each different observing mode, as well as on our Read the Docs page. I'll now go through each of the stages and kind of talk a little bit about the key TSO-specific modifications or algorithms that we needed to develop or transfer from Hubble or Spitzer and pipelines. At the stage 1, Eureka acts as a wrapper to the JWST pipeline, adding a few key specific TSO options or surfacing them from JWST. One is group level background subtraction, which is done column by column for most instruments, but can be done row by row for NearCam, which has 1/f noise in the other direction. And typically, this group level background subtraction works well when the number of groups is fairly small. We expose the jump threshold from the JWST pipeline because we were experiencing very excessive false positives and needed to significantly elevate the jump detection threshold to avoid throwing out a great deal of our data. Related to that, Tom Green and I are working with some people at NASA Ames to develop a machine learning, deep learning technique to automatically detect jumps with better false positives and better true positives. We also added tools to do expand saturation flags, either along an entire column to avoid missing pixels or bleeding in the spatial direction, causing issues, as well as expanding the saturation flag to the previous group in cases where partial saturation or nonlinearity weren't sufficiently handled or flagged by the pipeline, as well as a custom bias correction, which was useful for near-spec data. We have a couple alternative ramp fitting algorithms, which I'd rate as experimental. They're not super well tested, but some people like to at least explore those. And then most recently, I've added some 390 Hertz noise removal code to get rid of this periodic noise in MIRI, which I heard is actually also under development for the JWST pipeline. Moving on to stage 2, again, we act as a wrapper for the JWST pipeline. And really, in stage 2, we don't offer much beyond the JWST stage 2 pipeline. We primarily expose the ability to expand the cross-dispersion extraction height, which is useful if you want more background pixels. Both NearCam and NearSpec get cropped by the stage 2 pipeline by default. And sometimes that's fine, but sometimes you need the extra pixels to avoid getting self-subtraction from the star. We also allow you to turn on or off the photometric calibration step. Turning it off is typically good for TSO data because you can get things like electrons per integration, which gives you a good estimate of your photon-limited noise. But if you want to do photometric calibration to get an idea of what your stellar spectrum is, then you can also do that with Eureka. Moving on to stage 3, Eureka completely steps outside of the realm of the JWST pipeline, although in stage 3 we do things fairly similar to the TSO stage 3 in the JWST pipeline. In stage 3 through 5, our outputs are saved as X-array data files, saved as HDF files, HDF5 files. So this allows efficient reading and writing of files and documentation of outputs. And I'll go through kind of some of the more important steps in stage 3. It starts off with just kind of reading the data. It allows you to mask pixels marked as bad in the data quality array, as well as any user-provided bad pixels. It determines the mean position of the spectral trace by collapsing along the spectral direction, and then converts data to electrons to be able to compute uncertainties and to be able to do variance-weighted optimal extraction later on. Then we allow you to straighten any curved traces. NearSpec and NearCam both have quite curved traces. And so we allow you to straighten those. At present, only doing integer pixel sliding. This allows you to nicely put just a box aperture over the trace with minimizing variable slit losses, but also doesn't make you interpolate flux to roll the spectra by fractions of pixels, which can be potentially risky. We then perform column by column per integration background subtraction, and we at all stages of at all steps of stage 3, we output a lot of figures that can be used for diagnostics, and in our save files we also put a lot of the intermediate values to again validate your analyses. Then we track the spatial position and PSF width of the trace. This is really helpful to understand the temporal evolution of the pointing of the telescope. On the left here, you have an observation with fairly minimal drift, and it might not be worthwhile tracking this. But on the right, you have something with quite substantial drift. I mean, in fairness, we're talking about 1% of a pixel, but like it matters a lot when you're trying to measure exoplanet time series observations or something like that. And so in stage 3, we measure these two parameters. And from experience, it's better not to try and do some kind of fancy corrections here, and it's better just to measure these values and carry them on to the light curve fitting step to be able to decorrelate against these as covariates. Finally, we get to the spectral extraction stage. We first do a simple, just initial box aperture, which creates the orange spectra here. And then kind of shown by the speed limit, driving along that road, you have a couple speed bumps and a couple potholes, and you want to go pretty slow over that. But when we break out optimal spectral extraction to extrapolate or interpolate over bad pixels, this significantly reduces those kind of noise spikes in our observations. And we allow you to do optimal extraction using many different extraction profiles, but we primarily recommend using the median frame of all of your integrations, as this is a pretty good empirical estimate of your trace profile. And then finally, we save all of that as a couple X-array save files and move on to stage 4. Some of the key outputs from stage 3 are this 2D waterfall plot. If you're familiar with radio astronomy, you see a lot of these. You have wavelength along the x-axis, time flowing upwards on the y-axis. And so for this exoplanet observation, you see this baseline, and then you see the astronomical event, transit, or eclipse, and then a baseline after. And then simultaneously with that, you're getting these kind of covariates out of the reduction stage to be able to allow you to decorrelate your data later. Moving on to stage 4, we're basically just transposing our data. We go from thinking of multiple spectra to light curves of multiple wavelengths. We also do a couple other things in here, measuring drift or jitter in the spectral direction using cross-correlation, which works okay. It works better for near-infrared instruments that have some stellar lines. For MIRI, there's almost no lines. The pixels are so fat that you basically get nothing out of it. And in stage 4, we mostly focus on spectroscopic binning to reduce noise or get your light curves down to a single resolution element rather than a single pixel. And then we also do time series outlier removal. So stage 4, yeah, it's basically just chunking up that 2D light curve into individual spectroscopic light curves. And if you want, we can also produce a broadband kind of semi-photometric light curve. Getting into stage 5, you finally see that the developers are almost entirely exoplanet folks, and so our stage 5 analysis methods where we're fitting the light curves are designed for exoplanet observations. But stages 1 through 4 should generally work for any time series observations taken with NIRCam GRISM, NIRCam deep focused photometry, near-spec spectroscopy, MIRI LRS time series observations, and MIRI photometry. At present, we're missing NIRIS SOS, MIRI MRS, and the upcoming NIRCam DHS mode. So yeah, as I said, we're primarily exoplanet researchers, but most of this should work, especially if you have like a single bright object. If you're looking at cataclysmic variable stars or whatever, it should work. And if you get to stage 5 and you want to be able to contribute your own light curve fitting packages, feel free to open a pull request and work with us on how to add that to the pipeline. So stage 5, we focus on simultaneously fitting any systematic noise components with the astrophysical components. A lot of us worked on Spitzer and Hubble data before, and we kind of are pretty experienced with this. Spitzer was kind of a nightmare, as you can see up here. It had a lot of sawtoothing and jumps, and it was a lot worse than JWST is, but when you're trying to measure the really, really small signals of cold planets or small planets, even though JWST looks nicer, semi-often you're still trying to measure signals substantially smaller than your correlated noise, and so you have to do something about that. Looking at astrophysical models, you can fit transit, eclipse, and or orbital phase modulations with Eureka. To model transits and eclipses, we allow you to use the Batman or the Starry packages to measure things like transit or eclipse depth, stellar limb darkening, orbital parameters. To measure phase variations, you can either use the Starry package, which uses spherical harmonics across the face of the planet, or you can use just simple Fourier decomposition of sines and cosines. You can use these to measure things like day-night temperature contrast, the hotspot offset of the planet's hotspot. And then you can also use the Starry package to very precisely measure the shape of eclipse ingress and egress to measure the brightness distribution across the day side of the planet. Looking at systematic models, every instrument is unique, but there are systematics that impact all instruments alike, including past observatories or past and present observatories. These include spatial drift and jitter, which I said we mentioned in stage 3, the changing of the PSF width, which again we measured in stage 3, and Nestor mentioned that with those ERS near spec observations from Alderson et al., there was that mirror tilt event which showed up very clearly in the PSF shape. And so measuring these at an early stage really helps you out later on. Alternatively, you can use fine gutter information, but at present, Eureka doesn't support that, although I definitely I definitely intend to go spelunking later. You can also consider the impact of drift and jitter in the dispersion direction, and then there's kind of polynomials in time that might impact you. And so Eureka allows you to linearly detrend against all of these drift and jitter parameters. The first two are particularly useful. Again, the spectral drift jitter typically much less useful. And currently we're only doing linear detrending against those because that seems to be good enough. But if ever you think that's not good enough, let us know and we can add polynomial detrending. But like I said, the pointing stability and PSF stability is really quite great. And so it seems primarily a linear impact. And for those really nasty data sets, we also allow GPs, Gaussian processes, as a function of time to do what you can to remove systematic noise. Looking at some instrument-specific systematics, you'll see my bias here as someone who's primarily worked on MIRI and NIRCam. With MIRI LRS observations, we have these strong temporal ramps in the integration light curves, where at short wavelengths, you'll see that over approximately half an hour, the light curve will substantially decay. At kind of intermediate wavelengths, however, it is much flatter as a function of time. And to model this, we allow you to fit them with decaying exponentials of decaying or upward ramping exponentials. For the MIRI LRS, some observations, such as the ones shown here of WASP 43b, have really, really strong and really long duration ramps from 10.6 to 11.8 microns, which is exactly in between the coronagraph on the top and the 4-quadrant phase masks underneath it. The LRS slit this subarray is in a particularly unfortunate place where it has quite non-uniform background illumination. And so something, we don't know what, in some observations causes really bad ramps in these wavelengths. And at least for these observations, it seems basically unrecoverable. The 10.6 to 11.8 data is just gone. There's, at present, nothing we've been able to do to be able to predict what that ramp is and decouple it from any astrophysical variations, which is unfortunate. However, it's not clear what's causing this. Some observations have it, some don't. Some of the same star in the same position angle have it and the other doesn't. Don't know what's going on. For NIRCam, we've heard so much about 1/f noise. It's particularly nasty for NIRCam because that correlation is along the spectral direction. And so you end up with spectrally correlated noise that by the time you get to fitting light curves, you're done. There's nothing you can do. So you really have to go back to stages 1 or 3 to try and tackle this correlated noise. At best, in stage 5, we allow you to inflate your white noise estimate to account for excess noise, but it doesn't account for the wavelength correlated nature of that noise, which your retrieval folks are going to be pretty mad at you about. So some key outputs from stage 5. Again, all of these stages, lots of figures, lots of save files to make easy comparisons with different pipelines. Stage 5, we have this kind of fitted light curve. What are the residuals? You can use this middle figure to determine whether you have any residual red noise. And you can use things like corner plots to get your parameter estimates and covariances between parameters that you care about and parameters you don't care about. Stage 6 is kind of just staple it all together and put a bow on it, kind of a stage where you take all of those individual transit, eclipse, phase curve fits and put them together as a spectrum. So I've shown here transmission spectra and emission spectra stapled together from Eureka. But you can actually produce these kind of figures for any of the parameters that you fit as a function of wavelength. So if you want to see what the linear slope did as a function of wavelength, you can look at that. If you want to see what the impact of the PSF changing was as a function of wavelength, you can do that. And for MIRI, that was particularly useful because you can see at short wavelengths, the PSF moves more and changes size more than the long wavelengths, where it doesn't really seem to have anywhere near as much of an impact. And so, yeah, this is kind of the end of where Eureka takes you. You get these output astrophysical spectra, and you can pass them on to your retrieval friends or your retrieval codes to do things like this, where we found the significant detection of methane in the atmosphere of the warm exoplanet WASP-80b at greater than 6 sigma in both transmission and emission. This paper is currently under embargo, but I encourage you to check out the preprint on arXiv. This was, yeah, super exciting work to lead. So, kind of stepping back, looking at what impact has Eureka had so far. In the past 12 months, we've had 22 papers cite our work. We have just last week released version 0.10, and we're actively, eagerly working on version 1.0. Version 1.0 will primarily seek to not add new features as much as possible, but break backwards compatibility to allow us to better have forward maintenance and basically just solidify what we've done in all of the other stuff, and then future versions will work on adding new features. On GitHub, we have 33 people who forked our repository, 44 who've started. We've closed 285 pull requests, 253 issues, and in the past 2 weeks alone, we've had hundreds of people clone the pipeline and thousands of views of our GitHub page. And our Read the Docs page sees pretty consistently tens of people looking at the documentation page. And this is consistent with new users coming to learn about the pipeline, as well as returning users being like, man, how do I do that weird thing in stage 3 again? Some keys to our successes so far. One has been ongoing financial support throughout all this development and maintenance. Initially, funding was provided by Early Release Science and GTO data. I in particular was funded by GTO stuff, Kevin Stevenson by ERS, and other people by different sources. And we also had a lot of early career researchers who just volunteered their time, their PhD work. The developers are people that are wanting to actively use the software on their own science data, and so they're really invested in contributing their own patches to the pipeline so that other people can benefit from that. The pipeline is open source and modular, which makes it easier to maintain. It's extensively documented, which again makes it easier to maintain and learn. And it has tutorials, making it easier to onboard new people. We've also presented 2 workshops at the Sagan Summer Workshop to help hundreds of people learn to use the pipeline. There's been broad interest from the community to use and learn how to use the pipeline, as well as ask help, because even if the documentation and tutorials are good, but like it's never going to be good enough, and so someone's going to have a weird like, oh, I got the new M3 MacBook yesterday. I'm the first person to run it. It crashes. Like, well, we can't possibly know that that's going to happen, but if you tell us that happens, then we can work with you to try and fix it. And so paired with that, it's taken a lot of willingness of us Eureka devs to be willing to support those help desk issues. One significant advantage of Eureka 2 is that it's substantially automated from end to end, which allows you to do things like, if new data comes down tonight, I can set up 15 different analyses, run them overnight, wake up in the morning, have 15 different astrophysical spectra, and I can be like, yeah, this one seems reasonable. It has a good background subtraction, didn't over-subtract, didn't under-subtract. And there you go, retrieval people. Here's my like kind of first shot analysis. Give me a week to like really fiddle with things, but like this is a pretty good first start. this also is reflected in testing, where every pull request gets automatically tested on GitHub, which helps Kevin and I moderate peer review pull requests. Early on, there was extensive cross-comparison between different time series analysis custom codes as a result of ERS and GTO efforts. And that's really helped us understand what are the important steps of TSO analyses versus like, it doesn't really matter what you do. So looking forward, we've gotten archival research funding from JWST Cycle 2. We'll seek to add nearest sauce support, most importantly, because that's used for a lot of TSO exoplanet observations. We're also hoping to add MIRI, MRS, and NearCam DHS support. We want to enhance light curve fitting, enhance reduction code, and continue to support users in resolving bugs, adding features based on people's experiences with Cycle 1 data. Yeah, one of the main things we also want to do is kind of reorganize the code to be a little bit more like the JWST pipeline. When we first started, we didn't understand the JWST pipeline, didn't understand its appeals, and since then we've come to realize how good some of the JWST features are, and we want to reflect that more in our layout. And then, yeah, looking forward, we're going to need more funding or some kind of support to keep this thing living for decades. And so potentially support from STSAI folks and other potential archive research funding will help maintain it and help onboard new people. And I'll end the talk there. Thank you.
Awesome, thank you. There are lots of good questions. I'm not even actually going to try to go through them here, but you can address them. I will just say thank you for supporting the community in this way, in humanity, so that they can see all these beautiful exoplanet spectra. So yeah, I think we'll stop there.
Cool.
Marco is going to show something. I want to say, since it's the last break of today, the voting officially begins on the Advise Us. I see some of you have been voting in advance using whatever symbols you want. That's fine. So remember, the game plan is you have 5 votes for the things that have been proposed in the Advise Us thing, and you're going to tell us what you think the best enhancements are from your perspective of the ones that have been proposed, and it's not too late to put another one in there. And now I will hand it over to Marco.
There have been many questions on how we're going to structure the day for tomorrow and Friday for those that stick around. So this is the agenda. We will use tomorrow morning with more detail, just to let you know that we're going to break down just after 30 minutes introduction of how you expect the exercise to go tomorrow. And these are the exercises that have been organized so far with the topic. And for each of them, there should be a dedicated channel on Slack, topic underscore, and something that's fairly close to 1/F at TSO pipeline and so on. If you don't find it, just browse the channels and you can join it if you want. This is location. Local people can clearly go around the building with no issues. External people should have received a magnetic card to access to and go to the boardroom. I think it's the only meeting room that is by this floor. And you have the contact person for that exercise. No, there is one additional exercise list that is floating on the choreography, and Julien, Jonathan, and Elle are sitting together. Sometimes just look at the current structure again. If you want to participate on some of the already planned exercises, planning in another time. It will be really hands-on exercises, so people that are sitting down around the table and trying to run the pipeline, their own version of the tools or the step on specific data sets. And there are long sessions of 3 hours. but the coffee will be served user place, so each SSI is free to break whenever they want. Take a break and go back. Tomorrow we'll go into some more details, but since there were been many questions, tomorrow which group I can go if I'm here it is.
So yeah, just to add, the different groups are doing different things because each area has, is in a different state. So, and some of them, it's still to be formulated exactly what they'll be doing. So if you feel like you don't understand exactly what a group is doing, it might be because that group hasn't quite figured out how they're going to use their time. Does anybody have any questions about this right now? Yeah. Yeah, so one of them says ask Jeff, and the two people that are allocated to that group are remote, and so I was planning to do it from my office, but I think Marco is smarter than that, and so he realizes that some local people not signed up people might be interested, so we will add a venue to them just so people who were not originally identified know where to go if they're interested. Other questions? Yeah. Yeah. Are there instructions about prep? So if you haven't received any yet, then there are not any yet. And that's true in most cases. I mean, there's been some discussion about what data sets to look at. It's the base plan is compare the latest pipeline products with whatever other things we might have available. So having the latest pipeline available is probably a good idea. But, we'll see. All right, let's go have the break and be back at 3:40. I'm constantly trying to subtract 1 minute from the clock in the back, so 3:40.